I can get to some actual quantum levels from the semi-classical orbit by using the Bohr-Sommerfeld quantization condition, basically demanding that the phase I accumulate around an orbit is an integer multiple of 2 pi, and the phase is just the energy of the orbit times the time, semi-classical time it takes to circumnavigate the orbit. And here, the time has two components. One is how long it takes to slide along the arc, which is the arc distance divided by Lorentz force. And the other is how long it takes for me to kind of come up, or propagate on this chiral lambda level through the bulk, which is just the thickness divided by the bulk velocity. And we can see two regimes. The first is that weak magnetic field. We can ignore this bulk component. And these energy levels look a lot like a conventional 2D Fermi surface. And there we expect quantum oscillation. And you can find that actually the magnetic field at which these levels cross the Fermi surface is initially regularly spaced. And the frequency of these oscillations, which has the units of area in momentum space, can be interpreted as follows. So if I start with zero doping, so I start right at this bulk Weil node with my chemical potential, I'll just have a bulk Fermi surface, it will just be a point, and I'll have these arcs connecting it. The solid line on the top surface, and there's a dash on the bottom. Now if I dope to a finite density, the bulk points become little pockets, and the arcs move outward and connect them tangentially. And the relevant area is actually the area that I sweep out and going from this zero doping arc to this other one, minus whatever's missing in the middle. So that sets this quantum oscillation frequency. And at larger fields, so namely when the field becomes much larger than the arc length over the thickness of my sample, you can basically ignore the arc part of the orbit, and the orbit is roughly just the electron bouncing this finite size level, bouncing back and forth up the sample, and I get no longer periodic structure with magnetic field, so the quantum oscillation speed. So these quantum oscillations and their kind of characteristic thickness dependence give me an experimental signature of this bulk boundary correspondence in this material. So the fact that the surface arcs are topologically tied to this bulk chiral lambda level. And you can reveal it in various ways. One simple, at least as a theorist way, is to imagine just changing the magnetic field orientation and tracking the position of these peaks in the density of space. And you see that there's a part that depends on the angle of the field, but actually the thickness-dependent part will not depend on the field. And so this thickness-dependent kind of offset of the phase of these quantum oscillations, you can track it precisely, in principle reveals the fact that you have this orbit that goes through the bulk. So it's kind of like a way to measure the topology of this orbit. And so one thing, as we move towards the kind of experimental part of the discussion, is that an important practical consideration always in quantum oscillation measurements is disorder. And in particular, you need to be able to complete the orbit without substantial scattering that will dephase the orbit if you want to get coherent quantum signatures out of it. So fortunately, in a lot of these Dirac materials, the mean free path can be actually very long, and the scattering times, be it quantum or transport times, are very long. And I'll say a bit more about this once we get to the experimental part. And just to kind of recap something Sid was mentioning, is that a related measurement is to look at cyclotron resonances associated with these orbits. That's basically the same story, but here if I drive in a field with some kind of electromagnetic waves, the electric field can kind of resonantly drive these orbits if you choose the right frequency. And the cyclotron frequency will also saturate at large fields, and this saturation frequency is dependent on the thickness of your sample. And moreover, you can see that there's a polarization dependence. If I drive perpendicular to the arc, the electrons on the arc can absorb energy from the field. So the electric field is along their velocity. But if I put the electric polarization this way, they won't absorb very much energy, so there should be a characteristic polarization versus arc orientation independence. Yeah, and it's kind of tantalizingly mentioned. There's a cute trick of making a very surface-sensitive probe out of this. I guess you'll have to ask. All right. So with this kind of simple semi-classical theory of these Fermi arc quantum oscillations in hand, I want to turn to some recent data measured in James Analytis' group, and the postdoc really championing this measurement is Philip Moll, who will be moving to faculty position in the MPI in Dresden. So they developed this really cool way to make microstructures out of cadmium arsenide. And this picture is a bit hard and has some optical illusion-like elements to it, so let me walk you through it. So what they do is they start with a thin film of cadmium arsenide, and they take a focused ion beam, and they can basically carve out sections that they don't want. And so these dark shaded sections are pieces that they've carved out with a focused ion beam. And you can see that they leave in these holes a thin film of cadmium arsenide kind of standing on its side compared to the pictures I've been drawing so far. So these little purple sheets or thin film standing on their side. And they can control the thickness of this kind of freestanding membrane piece. And also its geometry just by changing kind of the angles of the fabrication, the ion beam milling, or yeah. So the nice thing about this fabrication technique is that the ions are incident from the top. So they're actually come in at grazing incidence to the surface. They have the effect of actually cleaning off the surface as they come down, so that any kind of junk sticking out will get blasted off. They get very nice surfaces on these side surfaces. The top surface is junk, but in the way they've fabricated it, this is not the important surface for surface phase. And the other nice thing is that both surfaces have basically the same fabrication parameters, and so they'll be roughly the same. Okay, so the measurement they do is to run current through these devices in a field. And so let me start with the field. You can orient the field in any angle you like. And if the field is perpendicular to the surface, so that's 0 degrees, you see this large transverse magnetoresistance that's characteristic of these materials, and on top of it some quantum oscillations, which if you analyze, you see two frequencies, say this first peak and the second peak, which has some weird stretched line shape. And if I turn the field parallel to the surface, I only see one frequency. So these little double peaks here are actually spin splitting of the bulk Fermi surface. But if I Fourier transform, I can clearly see just one bulk, so one frequency. And moreover, as I change the angle of the field continuously, I can watch what happens to these two peaks. And this one that I'm calling FS has some characteristic 1 over cosine theta dependence, which clearly marks it as a surface state. And the bulk, this blue peak, is actually a bulk pocket that's roughly symmetric. And so this is really characteristic or suggestively depicted in this polar plot, where here is an angle, the polar plot of the frequency versus angle. So the question is, what's the source of this surface signal? Is it related to the Weil oscillations that I was talking about in the first half of the talk? And to do this, I have to address the elephant in the room, which is related to Youngbeck's question, which is, so cadmium arsenide is actually a Dirac semimetal, it's not a Weil semimetal. So what is the role of this crystal symmetry requirement in the protection, and how does surface states of one of these Dirac semimetals look? So naively, if we picture the Dirac semimetal as two copies of Weil semimetal protected by crystal symmetry, you expect two sets of arcs. One from the one kind of crystal symmetry representation and one from the other, dispersing the opposite way. And generically they'll meet at the bulk Dirac point. The problem is that the crystal symmetry protecting the bulk nodes is actually some rotation symmetry along the axis separating them. So any surface that you would expect to see